Welcome back. Today, we're going to have more fun with chemistry math. Have you ever had to write a really long number and wish there was an easier way to do it? Well, sometimes there is. That is what we are going to discuss today, an easier and shorter method of reading and writing numbers with a lot of zeros. First, let's try to imagine why this would be so important in a chemistry class. Remember, chemistry is the study of matter. Matter is made up of atoms, and atoms are very small. Let's see if I can get you to begin to imagine just how small. Suppose we have a cube of copper that is 1 inch on each side. This cube would have 100 million atoms on each edge. That means that each surface of the cube would have 100 million times 100 million atoms. Now that's a very big number. Since we study atoms in chemistry, you can see that learning an easy way to represent really big numbers will be useful to you. So let's be sure to have your calculators ready, and we'll begin.
During this lesson, you will express numbers in correct scientific notation, convert from scientific to decimal notation, convert from decimal to scientific notation, and use your calculator to work problems in scientific notation.
You can see from the example of the copper cube that numbers are sometimes so big that it takes a lot of zeros to write the number in decimal notation. That's when scientific notation comes in handy. You know that sound means take good notes, because this is important. In scientific notation, measurements are expressed in this form: m times 10 raised to the n power, where m is a number that is greater than or equal to 1 but less than 10. Because the 10 is raised to the n power, scientific notation is often called exponential notation.
Let's go through some examples and see if we can figure out which ones are in the proper scientific notation form and which ones are not. We also need to determine what is wrong with the examples that are not in the correct form for scientific notation. You should jot these down in your notes as we go through them, so you will have something to refer to when you study later.
Our first example is 9.2 times 10 to the second power. What do you think? If you look at the rules for scientific notation, you will see that this is correct. The first amount is 9.2. This amount is greater than or equal to 1 but less than 10. It is also being multiplied by 10 and raised to a power. This is, in fact, the correct form for scientific notation. Our second example is 0.4 times 10 to the negative 14. Does this look correct to you?
This one is not in correct scientific notation because 0.4 is not greater than or equal to 1. When you start playing with scientific notation on your calculators, you'll find that when you enter a number like this one in your calculator, the calculator will automatically put it in correct scientific notation.
What about the number 1.8 times 2 to the fifth power? Is this one in correct scientific notation? Remember that the correct form is times 10 raised to a power, so this one is not correct. Now try 860 times 10 to the negative 3. This one is not in correct scientific notation because 860 is not less than 10. Your calculator may correct this one for you as well. Finally, try 9.898989887 times 10 to the first power. This one is in correct scientific notation, even though expressing this number in scientific notation does not save any room or make anything simpler or easier. Still, it is in the correct form for a number in scientific notation.
Now you will learn to change a number from scientific notation to decimal notation.
Before we do that, I can see that some of you have a rather quizzical look on your faces. I know it's easy to get bogged down in the math and start to tune out. So let's look at a prime example of just how important this math skill is to a chemistry student. Here's a number that you will become very familiar with this year. It's called Avogadro's number, and we will talk about its purpose in detail in a future program. Wow! Think of what a pain it would be if we had to write this number out every time you used it. I can already hear you complaining, my hand hurts from all that writing. Okay. Let's make your life much easier by learning how to change numbers into scientific notation.
This number's in scientific notation, and you're probably familiar with scientific notation by this time in your high school career, but you may have learned one set of rules for putting a number into scientific notation, and then another completely different set of rules for taking it out. That can be confusing. You can forget. So what I want you to do is really understand what the power of 10 means. So when you see this, what does this 10 to the third tell you to do?
Multiply by 1,000?
That is correct, but we want to be even more general because this could be 10 to the 14th and you don't know a number for that. So what if I said 2 to the third? What does that mean?
2 times 2 times 2.
That's right, you multiply by 2 3 times. So what does 10 to the third mean?
10 times 10 times 10.
That's right. So we take this 2.1 and we simply do what it says. We multiply it by 10 how many times?
3.
3 times. Good. And how do we multiply a number by 10?
You add zeros?
Not really, because the first time you multiply by 10, remember you're going from this side to this side, and so you'll really only add 2 zeros. So let's be a little bit more specific on this one. How do you multiply by 10 3 times?
Move the decimal.
And which direction?
Right.
To the right, okay? So you'll move it to the right. All right, now what if I had -3 here?
1 over 10 to the third.
That's exactly right. You remember your math. So this is 1 over 10 to the third, and that's multiplied by 2.1. And so what does this really tell you to do?
Making the number smaller.
Making the number smaller, and you're going to divide by 10 how many times?
3 times.
3 times. And which way are you going to move the decimal?
To the left.
To the left to make the number smaller. Okay, good. Now, all this probably seems very obvious to you, but you'd be surprised how many students memorize their way through it, never really understand it, and then they forget or they make silly mistakes. So I really want you to understand it. So let's practice doing one. Here we have 6.2 times 10 to the fourth. Susan, what does the 10 to the fourth tell you to do?
Multiply by 10 4 times.
4 times. So we're going to take our 6.2, we're going to move this decimal to which direction?
To the right.
To the right. How many times?
4.
4. Good. 1, 2, 3, 4. This is where our decimal will wind up, and what do we put here to hold the decimal place?
Zeros.
Zeros. So we wind up with 62,000. Okay? One more. All right. Now we have 1.5 times 10 to the negative second power. What does that tell you to do?
Divide by 10 2 times.
Divide by 10 2 times. And for that, we'll move the decimal. Which direction?
To the left.
To the left. 2 times. 1, 2. Put a 0 here to hold the decimal. And our answer is 0.015. Easy?
Yep.
Piece of cake.
That's easy enough. Now it's your turn.
Your local teacher is going to put the following problems on the board for you to work. When you have finished working the problems, I will come back to go over them with you. Local teachers, please pause the tape now and give students time to work program 1-3, problem set 1.
Let's check your work. In A, the times 10 to the negative 5 tells you to divide by 10 5 times. This moves the decimal to the left 1, 2, 3, 4, 5 times. Fill in the extra spaces with zeros. And the answer is 0.000024. The 0 before the decimal is there to call attention to the decimal in printed materials and is optional. For B, we multiply by 10 3 times, moving the decimal to the right and making the number bigger. The answer is 7,060. In C, we multiply by 10 6 times. 1, 2, 3, 4, 5, 6. Fill in the zeros. In decimal notation, the number is 6 million. In your textbook, spaces are used instead of commas to separate the groups of 3 zeros. So, 6 million might look like this in your book. In D, we multiply by 10 twice. This makes the number in decimal notation 194.9. Notice that the non-zero digits are never replaced by the power of 10. Finally, in E, the times 10 to the negative 1 tells us to divide by 10 one time. This makes the number smaller, so we move the decimal to the left one time. The answer is 0.25007. Remember that the 0 before the decimal is optional.
Now you will learn how to change a number from decimal notation to scientific notation.
Hello! I see some of those funny faces out there again. You're getting bogged down in the math again, aren't you? Well, stay alert because we've still got some important things to do. Things that will really help you as we go along. Let's look at a couple more examples of some numbers related to chemistry that will eventually make you glad you're learning scientific notation.
Check out the mass of one electron. Or think about how many atoms are in a single grain of sand. Or a penny. Now, how are you going to manage all these numbers until you learn how to put them into scientific notation?
All right, once you're comfortable taking a number out of scientific notation, it's pretty easy to put it into scientific notation if you'll just pay real close attention to what you're doing. So, let's start with 8,500. Now, for proper scientific notation, where does the decimal need to be?
After the 8?
That's right, we want it to be after the 8, so we're going to make this 8.5. So we're going to put it right after the 8. Now, where is the decimal really?
At the end.
That's right, even though you don't see it, it's at the end. Now, we don't want to change the value of this number. We don't want it to be 8.5, we want it to be 8,500. So what will we have to do to this 8.5 to change it into 8,500?
Multiply by 10 3 times.
That's right, we'll need to multiply by 10 1, 2, 3 times. Times 10 to the third. And that's it. All right, let's try this one. We want to put it into scientific notation. Now, where should the decimal go for correct scientific notation?
After the first 3.
That's right, so we're going to put it right here. The number's going to become 3.03 times 10 to a certain power. All right, now we can actually see where the decimal is in this one. It's right here, but it doesn't really belong there. We can actually see where the real decimal is, and your job is to start where we put the decimal arbitrarily and move it to its real location. So you're moving toward the decimal like it's a period at the end of a sentence, okay? So what will we do?
Divide by 10, 1, 2, 3, 4 times.
4 times. So we will write times 10 to the what?
Negative 4.
Negative 4. Just right.
It's time to practice. Your local teachers will put these problems on the board for you to work. Put the numbers into correct scientific notation. When you are finished working, I will go over the answers with you. Local teachers, please pause the tape now and give students time to work Program 1-3, Problem Set 2.
In A, we put the decimal here because 6.011 is greater than 1 but less than 10. Now, to turn 6.011 into 6,011,000, we need to multiply by 10 1, 2, 3, 4, 5, 6 times. So the number in scientific notation is 6.011
times 10 to the 6th power. B is 0.058. In scientific notation, we'll put the decimal after the 5 to be expressed as 5.8 times 10 to some number. What do we need to do to turn 5.8 into 0.058? We'll need to divide by 10, since we're moving to the left, 2 times. In scientific notation, the number is 5.8 times 10 to the power of -2. In C, the number in scientific notation becomes 3.5 times 10 to the power of 1. D becomes 9.009 times 10 to the -3. Since we would need to divide the 9.009 by 10 3 times to get to our original number of 0.009009. E looks like a trick because it is already a number between 1 and 10. In scientific notation, this number is 6.732104 times 10 to the power of 0. If we do not move the decimal at all, we give the base of 10 a power of 0. Remember, multiplying by a power of 0 is the same as multiplying by 1. Before we go on, let's look at the numbers I mentioned before. You know, the ones that are going to help you appreciate scientific notation. Remember our copper cube with so many atoms on each surface? What would this number be in scientific notation? If you counted correctly, you got 1 times 10 to the 16th atoms. What would Avogadro's number be in scientific notation? Figure it out for yourself. We'll give you a few seconds to do it. This time, you should have gotten 6.02 times 10 to the 23rd power. By the way, as a matter of review, do you think Avogadro's number is a measurement?
Of course not. A measurement would have a unit.
Excellent. Now, let's try the mass of an electron. What would this number be in scientific notation? You should have answered 9.1 times 10 to the -31st kilograms. Now, let's try the number of atoms in a grain of sand and the number of atoms in a penny. You should be a pro by now. A single grain of sand has 1 times 10 to the 19th power atoms, and a penny has 6 times 10 to the 22nd power atoms.
So, you can see how it will be much more convenient for us to write these numbers, as well as many others, in scientific notation as we learn chemistry this year. Scientific notation is really fairly simple if you just stop to remember what the times 10 means.
Now it's time to learn how to do scientific notation on the calculator.
All scientific calculators have buttons that allow you to enter a number in scientific notation. On some, the button will be labeled EXP, and on many it will be labeled EE. An easy way to remember what this means is enter exponent. If you want to enter 1.5 times 10 to the second in a calculator, you punch 1.5, then the EXP button, then the 2. Or punch 1.5, then the EE button, then the 2. You do not need to enter a 10. Imagine a little guy who lives inside your calculator. He does exactly what you tell him to do when you punch the buttons. He understands that punching the EE button takes care of the times 10 to the blank power. When you enter the number in scientific notation, the display screen on the calculator will probably look like one of these. Again, the 10 is not displayed because it takes up space on the display. The base 10 is understood. Try this on your calculator. Multiply the product of 2 times 10 to the third times 4. You should get the answer 8,000. Most calculators will put the answer in decimal notation if there are enough spaces on the display. However, your calculator might have given you the answer 8 times 10 to the third. Is that correct also? Well, let's remember that 8 times 10 to the third means to multiply 8 times 10 3 times, which is 8,000. So yes, that is correct as well. Some of you may have gotten 80,000 instead of 8,000. In this case, you have made the most common error in entering numbers into the calculator in scientific notation. You typed 2 times 10, then the EE button, then 3. Calculator Guy did exactly what you told him to. He multiplied 2 times 10, and then multiplied his answer times 10 to the third power, because that is what punching the EE button and then 3 tells him to do. Remember that the EE button takes care of the times 10 to the blank power. Don't enter the extra 10, or your answer will be 10 times too large.
Let's practice to make sure you've got it. You do not need to write the problems down. Just enter it into your calculator to see if you are entering it correctly. Try 6 times 10 to the fourth power times 5 times 10 to the eighth power.
You should have gotten 3 times 10 to the 13th power. If you didn't, show your local teacher or another student what you entered so they can help you fix the problem. Now that everyone has figured that one out, let's try one more. 3 times 10 to the negative third power divided by 6 times 10 to the fourth power. You should have gotten 5 times 10 to the negative eighth power. Now let's try one of our previous examples. Remember our copper cube? We multiplied 100 million times 100 million to find out how many atoms would be on each surface. Convert each of those numbers to scientific notation and punch them into your calculator. You should have gotten 1 times 10 to the 16th power as the number of atoms on each surface. If you missed this one, get with a neighbor and figure out why. Local teachers, you may wish to pause the tape for a few minutes if you feel your students need extra time to review their mistakes.
Now let's combine what we have learned about measurements with what we have learned about scientific notation. Suppose we have a block with the dimensions 12.5 centimeters by 8.3 centimeters by 4.2 centimeters. What would be the volume of the block expressed in correct scientific notation?
Well, you need to use the formula that says that the volume of a rectangular object is equal to its length times its width times its height. So I multiplied 12.5 times 8.3 times 4.2 to get 435.75, which is 4.3575 times 10 to the second power.
Very good, except I think volume is a measurement, and your answer is just a number.
Oops, I mean that the volume is 4.3575 times 10 to the second power centimeters cubed.
Excellent! However, I think now might be a good time to talk about reading numbers off of our calculators. Believe it or not, your calculator may be too accurate. If you just copy all of the digits that your calculator reports, then your answer will be more accurate than the measurements you started with. In this example, our ruler allowed us to measure to the 10th place, but our answer measures beyond the 10th place. For now, let's use the rule of thumb that our answer should have the same number of digits as our original measurements. So, let's cross out the 575 and report our answer as 4.4 times 10 to the second power centimeters cubed.
Well, That's enough math for one day. Your math hat, like mine here, is probably beginning to get tired. But don't put it away yet, because it's time for your chemistry quiz. When you are finished, your local teacher will go over the answers with you. Here's cumulative review question number 1. In an experiment, the variable deliberately changed by the scientist is called A, the controlled variable, B, the manipulated variable, C, the responding variable. Pump up your tired math hat for cumulative review question number 2. What is the volume of a cube if each side measures 2.0 centimeters? A, 8.0 centimeters. B, 8.0 centimeters cubed. C, 2.0 centimeters. D, 6.0 centimeters cubed.
Number 1. Numbers in scientific notation must be expressed in the form m times 10 to the n power, where a, m is 1 and n is greater than or equal to 1 but less than 10. B, m is greater than or equal to 1 but less than 10 and n is 1. C, n is greater than or equal to 1 but less than 10. D, m is greater than or equal to 1 but less than 10.
Question 2. Which of the following is in correct scientific notation? 16.5 times 10 to the third. 3.0 times 3 to the third. 1.3 times 10 to the third. 0.54 times 10 to the third.
Use your tired math hat one more time for number 3. Express the number 0.0003 in correct scientific notation. A, 0.0003 times 10 to the first power. B, 3 times 10 to the fourth power. C, 3 times 10 to the negative fourth power. D, 0.3 times 10 to the fourth power.
Give the math hat a rest and use your calculator for question number 4. Multiply 3 times 10 to the second power times 2 times 10 to the negative third power. A, 6 times 10 to the negative first power. B, 6 times 10 to the first power. C, 6. D, 6 times 10 to the fifth power.
Okay, little fella, relax for now. Be sure to give your math hat a little rest, but not for long, because I want you to spend some time practicing the skills you've learned today. Your math hat can help you ace your next quiz. So until we meet again, take care of your hat and enjoy your chemistry math.